Hello, welcome to the course Understanding Electricity and Electronic Devices by Clean Motion. Today, we're going to talk about the bipolar transistors. This would be our second class on transistors. As usual, let's start with a review of some concepts that we saw on our last class. Transistors are three-terminal devices, and the three terminals are called collector, base, and emitter. Collector current is many times larger than the base current, about 100 times or more sometimes. And collector and emitter current are about the same. The collector usually works as a constant current source, but if you solve a circuit and you end up with a voltage between collector and emitter that is negative, the result is not true because the transistor is no longer working as a current source. We see that the transistor is actually in saturation, and the collector to emitter voltage is going to be closer to 0.2 volts or something like that. So today we're going to see how we can use a transistor as a switch. We're going to see how we can drive a relay with a transistor, and we'll see a simple circuit that can turn on the lights at dusk. And we'll also see some simple timer circuits with transistors. This is something we already saw on our last class as well. The base emitter junction acts as a diode, right? And when current flows, that's our base current here. And this is multiplied by a factor of beta or HFE, which can be in the range of 100 to 300. And that's going to be the collector current. So the base current controls the collector current. Let's have a look at this circuit and see how we can use an NPN transistor in a switching application. So we have an NPN transistor with a resistor of 100 ohms connected to its collector to a 5-volt power supply. The base is connected through a 1 kilo ohm resistor to variable voltage source that can deliver from 0 to 3.3 volts. Okay. If we calculate the base current is going to be the input voltage, Vn, minus 0.7 volts, which is the voltage at the base, divided by 1 kilo ohm, which is the value of this resistor. This base current is going to be reflected on the collector, but 100 times higher, right? Or multiplied by a factor of beta. Beta, like we said, can be in the range of 100 to 300. So we're going to have a collector current that is much higher. And finally, the collector voltage is going to be depending on how much current is flowing through this resistor. We have 5 volts here from the power supply, and we're going to lose on the resistor 100 ohms times whatever current we have on the collector. So 5 volts minus what we lose on the resistor is going to be our collector voltage. Mathematically, it's this equation here. So let's see what happens when we start increasing Vn, our input voltage, from 0 to 3.3. But first, our base voltage is 0, and our base current is 0 as well. That's this blue trace. Because our base current is 0, our collector current is 0 as well. So we have the blue and the orange traces overlapping here. When there's no current flowing through the collector, the voltage at the collector is going to be 5 volts because nothing is being lost on the resistor because there's no current flowing through the resistor. So that's the yellow trace over here showing 5 volts at the collector, okay? Now, as we increase the input voltage, that nothing is going to happen until the voltage at the base reaches 0.7 volts, right? So those same conditions that we had at 0 volt remain until we have about 0.7 volts at the base or at the input. From there, the diode of the base emitter junction starts to turn on, and the current through the base is going to rise, limited by this 1 kilo ohm resistor. So it's going to follow this curve, okay? So it starts at 0.7, and when we increase 1 volt, we are at 1.7, and the current is here about 1 milliamp, okay? So the slope of this one is 1 kilo ohm. We increase from this point 1 volt, and the current increases 1 milliamp. Now, that increase in base current is going to be reflected on the collector with an increase in collector current. Now, as you can see, the collector current rises a lot more sharply because of the gain of the transistor, which can be in the range of 100. Now, what happens with the voltage at the collector? So the voltage at the collector was at 5 volts until the transistor started to turn on. And from there, it went down because the current through the resistor is increasing, and the voltage drop on the resistor is increasing. So that is leaving less voltage at the collector. So the voltage at the collector drops from 5 all the way to about 0.2, which is where the transistor is going to saturate. And from there, it will not go down anymore. Okay? So what we're seeing here is that the transistor was completely off here up to about 0.7 volts at the input voltage. And then over here, it's dropping only 0.2 volts. So it went from cutoff, which is what we call this zone where there's no conduction, to saturation, which is this zone where the external circuit does not allow the transistor to conduct any further. Okay? So we can think of this transistor as acting as a control switch, right? So because from this point to this point, we increased the input voltage in less than 1 volt. So the transistor went from being completely off to being on. At this point, the transistor acts almost as a switch that is on, okay? And we managed to do that by varying the base voltage only by less than 1 volt, okay? When we use an NPN transistor in a switching application, like the circuit we just saw, the load goes connected to positive on one side, and the other side goes connected to the collector of the transistor. The load can work at a higher voltage than the controller. In the previous example, we were having the load was being switched at 5 volts, while the base was connected to a controller that could supply only 3.3 volts. And the voltage from the controller has to be enough only to saturate the transistor. In the example in the previous slide, it was about 1.2 volts, right? So it doesn't have to be powered by the same supply as the connector, as the load, right? So you could have a controller working with like 3.3 volts, and that controlling the load that requires maybe 24 volts, okay? Beta or HFE is not very important as long as it is high. So as we're going to see in a few slides from now, we don't know really what beta is, but we know it's going to be high, or we know what the minimum value is going to be, and we're going to be designing around that. And the other important thing is that the current supplied by the controller is low. In this case, we were having about 1 milliamp or a few milliamps supplied by the controller, and the collector current would normally be a lot higher, right? More than what the controller can normally supply. So let's see how we can use transistor to drive a relay. This is a fairly common combination, depending on what is it that is controlling the circuit, right? If we have, for instance, a microcontroller trying to control a relay, the current that a microcontroller pin can deliver is not enough to turn on the relay. So it's common practice to add a transistor in between. So this would be the circuit. The relay connected to 5 volts, and then on the other side to the collector of the transistor. And this voltage here would represent my controller and can output voltages between 0 and 3.3 volts. And that is connected through a 1 kilo ohm resistor to the base of the transistor. So as we saw before, this will turn on and off the transistor, and the controller only has to supply a few milliamps for this to happen, which should be well within the capabilities of this controller. Now, when you do these kind of things, it's a common practice to add a diode in parallel with the relay coil. And the cathode is going to be connected to positive and the anode to negative. So under normal circumstances, this diode would never conduct, right? Because this is more positive than this one. So the diode would be in reverse at all times. Now, if you recall from our class on inductors, when an inductor turns off, it wants to keep the same current. So the coil of a relay acts as an inductor in that regard. And if we have, say, 100 milliamps going through this coil through the transistor, and the transistor turns off, you can think of the transistor as a variable resistor that goes from a very low value to a very high value. And the coil is going to try to keep pushing the 100 milliamps through it, right? Because it's an inductor. And only that those 100 milliamps are going to be going through a much higher equivalent resistance here. That's going to cause the voltage at this point to shoot up, right? If we were trying to make a boost converter, this is something we would want to take advantage of, but this is not a boost converter. So we just want to provide a path for the current to discharge. And that is what this diode does. So when the transistor turns off, this node here goes positive to a high voltage, and that's going to turn on a path here for the current through the coil to dissipate through the diode. And that's going to limit the voltage here to 0.7 volts above the 5 volts that we have on the supply. If we didn't have this, the collector voltage can shoot up maybe to 100 volts or so, and that may be damaging the transistor. Relays are not the only kind of inductive load that transistors will be switching. Motors are other devices that can behave in the same way. So if we were controlling a DC motor here, we probably want to have a diode connected like this as well. Okay, so let's hit pause on transistors and let's talk about these devices that are called LDR. LDR means light-dependent resistor. They're also called a photoresistor or a CDS cell. CDS is called cadmium sulfide. That's the material that is used in these cells. This is what they look like, a two-terminal device, and this is their symbol. So how do these work? These are devices whose resistance varies with light. Okay, so when it is dark, the resistance is going to be high, maybe 200 kilo ohms or something like that. And in bright light, it may be about 1 kilo ohm or so. So these could be used as light sensors. Okay, this is a symbol, which is a resistor with these two arrows pointing to it, symbolizing that this would be the light and that this resistance is sensitive to light. These values that I gave you here are just a very rough guideline and could vary a lot from one unit to the next, okay? So check the data sheet or even measure them. to see how they behave if you have to design one of these. These LDRs allows us to build this circuit in combination with a transistor that could turn on the lights at dusk. Okay, so let's see how it works. Basically, this is the same circuit we had in the previous slide, with the transistor driving the relay with the diode for protection and 5-volt power supply. Only instead of having a controller here or a 3.3 variable voltage supply, we have a fixed resistor of 10 kilo ohms and an LDR over here. In bright conditions, assuming the resistance of the LDR is about 1 kilo ohm, this is forming a voltage divider with 10 kilo ohm resistor and 1 kilo ohm resistor. If you do the math, the voltage here is going to be around 0.5 volts. 0.5 volts will not be enough to turn on this transistor, and the relay is going to be off. Okay, so in light conditions, low resistance, low voltage here, and the relay is off. Now, when it gets dark and in complete darkness, the resistance of this one, let's assume, is 100 kilo ohms. Now, the voltage divider of the 10 kilo ohm and the 100 kilo ohm resistor is going to put about 4.5 volts here with no connection. Okay. Now, with the connection to the base, this is actually going to be limited by the base emitter diode at 0.7 volts. Okay. But the 10 kilo ohm resistor is going to provide enough current to the base to turn on the relay. Okay. So when it is dark, the relay turns on and the lights turn on. You can think of this in a different way. When it is dark, all the current from the 10 kilo ohm resistor goes to the base, and that makes the collector to amplify that base current and turn on the relay. When it is light, we are diverting current from the base directly to ground through the LDR, and there's not enough current going through the base to turn on the relay. Okay. Now, because we said that the characteristics of the LDR can change a lot, it may be best to replace that 10 kilo ohm resistor with a variable resistor of maybe 50 kilo ohms. So that way we can adjust the value of this resistor and control the switch point. So how much light we're going to have when the lights turn on and the lights turn off. Following a similar concept, we could use a capacitor and a resistor on the base of the transistor to build a timer, a simple timer here. So how does this work? Well, when the switch closes, the 100 microfarad capacitor charges to 5 volts, okay? When it opens, it will discharge the 10 kilo ohm resistor into the base, okay, lowering the voltage. At some point, the capacitor is going to be discharged and the relay is going to turn off. So this circuit should keep, and this depends on the transistor and the relay, but this circuit should keep the relay closed for about 3 seconds after you open the switch. Similarly, we could come up with an on delay circuit. In this case, when let's assume initially the capacitor is discharged, right? So the transistor is off and the relay is off. When the switch closes, the capacitor is going to slowly charge, and when there's enough voltage here to turn on the transistor, the relay is going to close. And that circuit here should give us about 1 second delay from the time we close the switch until the relay actually closes. So how do we design a circuit to use a transistor as a switch? So first, we determine what collector current would make the transistor to saturate. So depending on what we have connected on the collector, what resistance and what voltage we have there, there's going to be some current that's going to make the transistor saturate. After that, we determine the required base current based on the data sheet, or use an estimated beta in the range of 50 to 100. Then we use a base current of about 50% to 100% higher than the calculated on the step before to ensure saturation. Something to keep in mind is that power transistors can have lower DC gains or lower values of beta. So instead of having a DC gain in the range of 100 to 300, they may have a gain in the range of 20, around 20. Okay, so if you're using a power transistor, check the data sheet, and you may have to adjust this estimated value of beta. So let's have a look at the design example here. Let's drive a relay with a coil specification of 5 volts, 100 milliamps. We want to trigger that with a controller that outputs 3.3 volts. And we want to use a 2N2222 transistor. Okay, so this is the circuit, 5 volts to the relay. Don't forget the diode, and then the collector and emitter of the NPN transistor. This voltage supply is representing the controller that will give me 3.3 volts. And we want to calculate this base resistor, okay? So let's see how everything that we learned on the previous slide would apply to this circuit. We will consider an HFE or DC current gain or beta of 50, and we know that the collector current is 100 milliamps. If we calculate the base current, that's going to be the collector current divided by HFE, and that's 2 milliamps. But we want to have some margins, so we will use 4 milliamps. If we calculate the base resistor, that would be 3.3 volts, which is the voltage from our source, minus 0.7, which is what we lose on the base emitter diode, and that's divided by the 4 milliamps on the previous step. So that's going to result in a resistor of 650 ohms, and we're going to be using 680 ohms, which is a standard value, which is very close. Okay, so how do we select a transistor for switching? There are some parameters that we have to look at. The first one is the maximum collector to emitter voltage. So you have to make sure that the transistor can handle the voltage that your circuit will be using. For instance, if you're going to be switching circuit with a voltage of 24 volts, you probably want some margin there and use a transistor with the collector emitter voltage at least 35, 40 volts or maybe higher. The other one is maximum collector current, right? So if you want to switch a load that takes 100 milliamps, one transistor will be enough. But if you want to switch a load that takes 2 amps, maybe a motor, a medium-sized motor, that will require a bigger transistor, a power transistor. And make sure you check HFE or beta or the DC gain if it is a power transistor, right? So if you're going to be switching 2 amps, 3 amps, or whatever, power transistors have lower values of beta. So make sure you use that one in your calculation. And the last one, which may or may not be needed to be reviewed, is the switching speed, right? If you need your load to switch quickly, say in less than 1 microsecond or so, you would have to make sure the transistor is fast enough for this. Okay, so let's review what we saw today. we learned that transistors can be used as switches, and we learned also that the NPN transistor would turn off whenever the base voltage is below about 0.5 volts. If the collector circuit cannot deliver the current that the transistor wants, the transistor is going to be saturated. The base current for saturation will usually be in the range of 1 to 10 milliamps. And remember, if you are driving inductive loads like relays, motors, or something like that, you need a diode in parallel with the load to suppress these high voltage spikes. And that is all for today. I hope you learned about transistors used as switches. And we'll see you next time when we will keep going on with transistors, with other kinds of transistors that we will study next class. Thank you. Bye.